Hi, I'm Jack, and this is my Week 5 project on the MATLAB composite body. I like to start my projects off with the results, just so you know what my body looks like and what we're working towards. The shape I defined is three bodies. Two of them are identical, just flipped, symmetrical about the x1, x2 plane. It's similar to bodies I've used in previous weeks. I redefined it so that the axes were symmetrical in this one, and then also I flip-flop between using a rectangle and a cylinder there. I switched it to a rectangle this week. Um, with my vector field, I'll show in the next slide. I kind of try and aim to make it like a real world example where there's deflection over a beam, but I'll show that in the next slide. The volume and the surface area I calculate in later slides and show that they're equal, and then the other two, the left hand side and the right hand side of the divergence theorem, are equal to each other, and we will show that by hand shortly. So these are my bodies. Those bottom and top shapes are called frustrums. They're defined, their geometry, by B, the bottom edge length, A, the top edge length, and H, the height. The rectangle is also going to be A as the base, that square length, and then L as the height is how we define these shapes. So first is the vector field definition. I actually used a very similar reasoning and vector to week 2. My thought is that these are kind of like a fixed plane like on a beam, and so I'm going to do some deflection. I decided to make it in the x1 and x2 axis primarily because it's a loading force, but I tried to get everything in there and just kind of use a good example for the math so that it wasn't like easy and linear. So this was the function I defined. I then went on to find the divergence of the function, which was pretty easy and very similar to the case 1 shown in class. So there's our divergence theorem. When we end up, this is what our divergence looks like, our deflection rather. Up here, very important equation that we discussed in class. The purpose of this project is to find a vector field and verify the divergence theorem with it. So these are, that's the left hand side and the right hand side, which we'll solve shortly. First I did a quick area, a surface area and volume check. These were the results we got from the MATLAB code when we defined the bodies. I went through and I hand calced it using the equations, and we get the same thing. So we know that at least the geometry is good. If we have any problems with the flux, it's going to be those n1, 2, 3 functions, or how we define the vector field or scalar field. So this tells us geometries are good. Body 1, so this is that bottom frustrum. I only show body 1, I don't show body 3 because they're the same idea, just flipped. This is how we parameterize the geometry in previous weeks. Note that there's no top area because that's where the rectangle comes in, and for the composite body we don't want to account for that. This is the volume of the frustrum as we determined in previous weeks, but that's the equation I used. So now get to the important stuff. So we had the divergence of the vector field, and we can use that equation with the body defined here. We can plug that in to get our surface equation that we use in the code, the body.surface. The left-hand side, you're going to see is just the triple integral of the divergence of the vector field over the volume. So you'll see here, this is that equation at the top, which is that divergence vector for this body, and then the volume of the body that we got in previous weeks. This is a big long integral, and it simplifies down to be an exact number of negative 14.93 when you plug in A, B, and L, and H, the constants that are defined for the geometry. You also see down here, I showed, because the perpendicular vectors for these slanted faces aren't as easy as we've seen in previous examples, so I thought it's good to go over. So there's my vectors. The right-hand side is dependent on those vectors, so it's the surface area equation as defined by the vector field, which is easy to solve for. It's just some plugging in of the scalar field times the perpendicular vectors n over the area, and you end up getting the same thing. They check out for this geometry, and the same thing for the rectangle. This one was even easier, so very easy parameterization. The volume is a squared over L like a regular rectangle, but we solved for that previous weeks. Same thing. We did the divergence vector for this body, plug that in times the volume of the body, and here you can kind of see how it comes out. U minus V, this one's an easy to zero because it's going to be integral of U squared over 2 becomes 1, and it's just 1 minus 1 is this U minus V part, and this is just a constant that can come out. So that all goes away, and you're left with just this term. You get negative 16 for the left-hand side. You do the same thing with the vectors, n, very easy. And the scalar field vector, I forgot to write part of it here. It should be then times n, vector n times dA. I forgot to write a little bit there. And that's the end. So I go back to the results. I'll show you guys the MATLAB. So that was my 3 composite body, and here's the MATLAB. Oh, whoops. There we go. And let's run it one more time. So I added in a lot of debugging code down here because I was having trouble with the n1, 2, 3 vectors, and that's how I was able to figure out just kind of like where things were going wrong. I could see that the volume was right, and that at first the div v integrated over volume, that was right for my hand calcs, but this was wrong. So I was able to figure it out by these little debuggers as I went along.